before the first stars burned, before galaxies spun their spirals into the dark, the universe lay in silence. It was a silence unlike any known to human ears, not the pause between heartbeats, nor the stillness of a windless night, but the deep and infinite quiet of a cosmos not yet awake. Darkness stretched in all directions, without edge or boundary. Matter had not yet gathered into form. Light, though it existed in potential, had not been set free from the dense plasma that bound it. Time itself seemed suspended in a slow, unhurried breath. And then, somewhere in that boundless void, a ripple began to move. It did not rush, it did not flare, it drifted forward, carrying with it the first faint whispers of what the universe would one day become. This was the cosmic dawn, the moment the first stars were born from clouds of primordial hydrogen, piercing the darkness with light older than any world. It was a birth, but also a shattering, a breaking of the eternal stillness that had reigned since the Big Bang. Those first photons have traveled ever since, stretched and softened by more than 13 billion years of cosmic expansion. They are fragile now, so faint they lie hidden beneath the roar of nearer, louder signals, and yet they remain. They are the forgotten signals of the universe's youth, traces of a time when the first matter gathered, when the first threads of the great cosmic web began to weave. If we can learn to hear them, to separate them from the noise of our own age, they may tell us the story of our true beginnings. The question is, what do they remember? For most of human history, the night sky seemed eternal, an unchanging dome scattered with cold, steady lights. The ancients mapped its constellations, traced its motions, and gave names to its brighter jewels. Yet the heavens above them were only a fraction of the truth. The real universe, the one that existed long before the first stars, lay hidden, invisible to any human eye. It was not until the middle of the 20th century that science learned how to listen to the cosmos, not with vision, but with ears tuned to a spectrum no human could hear. In the summer of 1964, two engineers at the Bell Telephone Laboratories, Arno Penzias and Robert Wilson, were testing a new radio antenna. They were not searching for the origins of time, only for a cleaner signal for satellite communications. Yet from every direction, at every hour, their antenna picked up a faint, persistent hiss. It was the same no matter where they pointed, no matter what they removed, no matter how much they tried to account for noise. Unbeknown to them, across town at Princeton University, Robert Dick and his colleagues were preparing an experiment to detect exactly such a signal, the fading afterglow of the Big Bang. When the two teams connected their work, the truth emerged. They had stumbled upon the cosmic microwave background, a relic from when the universe was just 380,000 years old. The CMB was a revelation. It proved the universe had once been hot and dense, and that the light from that era still bathed all of space. Yet even this afterglow was only a chapter, not the beginning. Between the Big Bang and the birth of the first stars, there stretched a long, unlit age. Astronomers called it the Cosmic Dark Ages, a period when the universe held no sources of light, only vast clouds of neutral hydrogen drifting through the cold. For decades, this age seemed unreachable. The CMB marked the end of the opaque early universe. The first galaxies marked the beginning of recorded cosmic history. What happened in between was a silence in our understanding, the dawn before the dawn. Then, in the early 2000s, a quiet ambition began to take shape among radio astronomers. If the early universe was filled with neutral hydrogen, Perhaps its presence could be detected not through visible light, but through a single, delicate fingerprint in the radio spectrum, the 21-centimeter line. This emission, or absorption, occurs when the electron in a hydrogen atom flips its spin relative to the proton. Under the right conditions, these subtle transitions could be detected across the vast gulfs of time. It would be like hearing the faint rustle of leaves from a forest that vanished billions of years ago. The challenge was almost overwhelming. On Earth, low-frequency radio waves are drowned in noise. FM stations, television signals, mobile phones, even the planet's own ionosphere. To find the ancient whispers, one would need an instrument tuned not to the loudest parts of the universe, but to its most delicate and elusive, murmurings. In 2015, on a remote stretch of the Australian outback, the experiment to detect the global epoch of reionization signature, EDGES, began its work. Its antenna was small by astronomical standards, no vast dish or glittering array, but its location and design were chosen for a singular purpose: to listen for the global signal of hydrogen from the cosmic dawn. It would not image individual stars or galaxies. Instead, it would measure the average sky brightness at each frequency, searching for the faintest of dips, a sign that the first stars had begun to shine, altering the hydrogen gas around them. For 2 years, the team collected data. Night after night, they sifted through the interference, stripping away the blaring noise of our modern age, the hiss of the Milky Way, the warmth of the atmosphere. What remained, if anything remained at all, would be a voice from a time when no galaxies had yet formed. And then, one night, it appeared, a subtle trough in the data, centered at 78 megahertz. It was small, almost lost in the noise, yet persistent. It matched the frequency expected for hydrogen 180 million years after the Big Bang, the time when the first ultraviolet light from the earliest stars interacted with the surrounding gas. It was not an image, not a sweeping panorama of galaxies, but something far more profound, a single point in the darkness, marking the moment the cosmic dawn began. When the team first saw the data, they hesitated. Such signals were fragile. Things, a poorly calibrated amplifier, a stray reflection from the ground, or a passing satellite could mimic the same effect. They tore through every possible source of error. They replaced equipment, reanalyzed the data, and retested the model against hundreds of simulations, and still the signal remained. It was only then that the weight of it began to sink in. They were not merely looking back in time. They were standing at the threshold of cosmic history itself, listening to the faint breath of the first stars. But the signal carried another secret, one they could not yet explain. It was deeper, colder than it should have been. If their interpretation was correct, the hydrogen gas of the cosmic dawn was nearly twice as cold as predicted by standard cosmology, and that, they knew, could mean something extraordinary. For in that temperature lay a question as old as physics itself. Had they detected not only the first light of the stars, but also the first signs of a hidden force, one that had been with the universe since its birth, shaping its fate in silence? In the quiet room where the Edges team gathered to review their results, the data curve lay on the screen like a shadow across an endless plain, a shallow trough, barely discernible at first glance, but in its depth lay something no one had anticipated. The dip in brightness temperature matched the moment astronomers had been chasing for decades, the awakening of the first stars. Yet the depth of the trough was wrong. By every established model, the neutral hydrogen of that age should have cooled to about 207 degrees Celsius, cold enough to bite through steel, but still warmed slightly by the pervasive glow of the cosmic microwave background. Instead, the edge's measurement suggested the gas was colder by an extra 3 to 4 kelvins. On paper, it was a small difference. In physics, it was seismic. If real, it meant that some unknown process, something beyond the expansion of the universe, had siphoned energy away from that ancient hydrogen. The room fell into a kind of stunned stillness. Astronomy often deals with faint signals and long odds, but here was something else, a signal that should not exist. For decades, cosmologists had believed the thermal history of the early universe was relatively straightforward. After recombination, when electrons and protons joined to form neutral atoms, the primordial gas cooled as the universe expanded, following well-defined equations of adiabatic cooling. When the first stars formed, their ultraviolet photons began to interact with that hydrogen, allowing the 21-centimeter absorption signal to be imprinted against the background glow of the cosmos. It was a clean, elegant sequence until now. The depth of the EDGES signal was almost twice as strong as predicted by these models. The anomaly was like finding a familiar book with entire paragraphs rewritten in an unfamiliar hand. It did not erase the story, it altered it in ways that demanded explanation. The first suspicion was error. The low-frequency radio band is treacherous ground for observation. It is littered with the roar of the Milky Way's synchrotron emission, billions of times brighter than the signal the team was looking for. Add to that the constant interference from human technology, aircraft navigation beacons, distant FM stations, even reflections from the ionosphere. The edge's antenna itself was small and unassuming, a flat metal panel tilted toward the sky. Could it be that this humble instrument had been deceived by its environment? The team ran through every possible flaw: miscalibration of the receiver, ground plane reflections altering the spectrum, even minute temperature drifts in the electronics. They tried replacing components. They modeled the effects of every physical surface within range. The signature persisted, even when they deliberately altered their data processing algorithms to test its robustness. The trough refused to vanish. The persistence of the anomaly began to take on a new weight. If it was not an illusion, then it was a window, one opening onto something beyond the standard model of cosmology. The leading speculation came from a quarter that had long lingered in the background of cosmic research. Dark matter, dark matter, dark matter is the unseen mass that shapes galaxies and galaxy clusters, outweighing ordinary matter by a factor of 5. Its existence is inferred from gravitational effects, yet it has never been detected directly. By most theories, dark matter interacts with baryonic matter, the atoms of stars, planets, and people, only through gravity. But what if, in the early universe, dark matter had been more sociable? The EDGES anomaly seemed to require an additional cooling mechanism. One possibility was that dark matter particles had collided with hydrogen atoms, stealing away a fraction of their energy. If the dark matter particles were light enough, lighter than a proton, and if they carried even a trace of electric charge, they could have dragged the hydrogen to a lower temperature than cosmic expansion alone would allow. It was a radical idea. For decades, physicists had been searching for dark matter as heavy, inert particles, WIMPs, or weakly interacting massive particles. The edge's result hinted instead at something far more elusive, perhaps a milli-charged dark matter, capable of whispering to ordinary atoms without ever speaking loudly enough to be seen in a detector. not all were convinced. The scientific world thrives on skepticism, and the Edge's result faced intense scrutiny. Could the signal be the product of subtle distortions in the foreground modeling? Was it a feature introduced by the mathematical functions used to subtract the Milky Way's overwhelming emission? Other teams raced to check the result with independent instruments. The SARAS experiment in India, PRIZM in the Canadian Arctic, LIDA in the United States. Yet the philosophical shock of the result began to ripple through the community. If the hydrogen was colder than expected, then either our understanding of baryonic physics was incomplete, or a new form of matter had played a hand in shaping the earliest structures of the cosmos, in a universe where every equation for cosmic evolution rests on the initial conditions set after the Big Bang. Even a few kelvins of unexplained cold could rewrite the story. For some, the idea was both thrilling and unsettling. If dark matter could interact with ordinary matter in this subtle way, it might open a pathway to its detection. But it would also mean that the fabric of the early universe was more complex than the clean, sterile picture drawn by standard cosmology. Others considered more exotic explanations. Could primordial black holes, relics from the earliest moments of the Big Bang, have influenced the gas temperature? Could unknown radiation fields from a pre-inflationary era have bathed the hydrogen, altering its state? There were even whispers of scenarios in which our universe had interacted with another, leaving behind faint thermal scars. The EDGES team, aware of both the excitement and the skepticism, remained cautious. They knew that an extraordinary claim requires extraordinary proof, and that the next stage of investigation would need more than a single detection. Yet in the quiet hours, as they looked again at the curve on the screen, they could not help but feel the enormity of what it represented. A whisper from the edge of time had reached us. It spoke not only of the birth of the first stars, but of a deeper, hidden hand shaping the cosmic dawn. And if that whisper was real, it was telling us that the universe we thought we understood is colder, stranger, and far more mysterious than we ever imagined. The Edge's signal was like the faint echo of a voice carried on the wind, fragile, indistinct, but impossible to ignore. It was not a discovery that could be claimed and left alone. It demanded verification, interrogation, and a relentless peeling back of everything that could possibly disguise itself as the truth. In the world of radio astronomy, the enemy is not distance. The universe is always distant, but noise. Every observation is a contest between the ancient whispers of the cosmos and the deafening chorus of the present day. The Milky Way itself hums with synchrotron emission, a smooth and powerful wash of low-frequency radio light, tens of thousands of times brighter than the sought-after signal from hydrogen at the dawn of time. Above that lies the cacophony of human civilization, the sharp, narrow notes of FM broadcasts, the pulsing beacons of air traffic systems, the hiss of satellites crossing the sky. Even the Earth's ionosphere, the charged upper layer of the atmosphere, bends and distorts radio waves as they arrive, to find a dip of less than 0.2 of a Kelvin hidden. Beneath such a roar is like trying to hear a single drop of water fall in the middle of a storm. The Edge's team had already spent years stripping away these layers of interference before announcing their result, but now the pressure was greater. If the signal was genuine, others would need to see it too, with different instruments, on different continents, under different skies. In India's remote Rajasthan desert, the SARAS experiment began its own careful listening. The team's approach was to place their antenna on the still waters of a lake, using the natural mirror of the water's surface to minimize ground reflections that could distort the incoming spectrum. The Canadian PRIZM project set its antennas on the frozen tundra of Nunavut, far from urban radio interference, where the polar night cloaked the land in months of darkness. In the American Southwest, the lighter array deployed dozens of antennas to map the low-frequency sky with unprecedented coverage, building a detailed portrait of the foreground emission so it could be mathematically subtracted away. Each team faced the same problem. The foregrounds are not merely brighter than the cosmic signal, they are smoother. The edge's signal, if real, is a sharp notch carved into that smoothness. Any error in how the foreground curve is fitted can either erase the notch or, more dangerously, create one where none exists, to peel away the static. Astronomers use mathematical models of the Milky Way's emission, fitting them to the observed spectrum. The smoother the foreground model, the more confidence they have that any remaining deviation is truly of cosmic origin. But if the model is too flexible, it can twist itself to fit even the faintest statistical bumps, making an illusion look like a discovery. This is the knife edge of cosmological radio work, the balance between removing what is not the signal and preserving what is. The Edge's team defended their analysis with rigorous tests. They rotated the antenna to different angles and times, ensuring the signal's frequency, position did not shift with the motion of the sky, a telltale sign of local interference. They built simulations to model the interaction of the antenna with the ground plane beneath it, ensuring the dip was not the product of reflections from the Earth itself. They even inserted artificial signals into their own data streams, just to prove they could recover them under the same processing conditions. The signal remained, but peeling away the static was not only a matter of hardware and mathematics, it was a matter of replication. Science is built on the principle that extraordinary results must be seen by independent eyes. This meant waiting. Radio astronomy at these frequencies is slow, seasonal, and unforgiving. Each site has its own challenges. In the Arctic, the deep cold tests the limits of electronics. In India, seasonal monsoons interrupt operations. In the desert, dust storms and heat strain both equipment and observers. Yet across the world, data began to accumulate. Preliminary reports emerged from SARAS, from PRIZM, from LIDAR. Some found no matching dip at 78 MHz. Others saw faint hints, but with too much noise to confirm. The tension grew as Edges, seeing something the others could not, or was. The anomaly, a phantom born of its unique design. To answer this, the community turned to another source of truth: simulation. If the Edge's signal was real, it should fit into a coherent picture of cosmic history. The density of hydrogen, the timing of star formation, the rate of reionization. Computational models were run with billions of virtual atoms, photons, and dark matter particles evolving across hundreds of millions of years. These simulations showed that an absorption signal of such depth required something beyond standard astrophysics. It could not be explained solely by the first stars heating there. Surroundings, dark matter cooling, remained the leading candidate. But the models demanded specific conditions. Dark matter particles must be light, no heavier than a few proton masses. They must carry a fractional electric charge to enable weak interactions with hydrogen. Their density must have been high enough to leave a measurable effect in the first 200 million years, yet low enough to avoid violating other cosmological constraints. It was a precise, narrow window, but one that some physicists believed was possible. Meanwhile, instrument designers began dreaming of a new generation of detectors. What if radio telescopes could be placed on the far side of the moon, shielded forever from Earth's radio noise? What if swarms of small autonomous antennas could be deployed across deserts, mountaintops, or even in orbit? The Square Kilometre Array SCAR, a massive international project under construction in Australia and South Africa, promised to push this frontier even further, mapping the 21-centimeter signal not just as an average across the sky, but in 3 dimensions, revealing the cosmic dawn as a living landscape in time. But these were dreams for years ahead. For now, the peeling away of the static was painstaking, incremental, and deeply human. Long nights in remote locations, recalibrating equipment in the dark, running the same processing scripts 100 times to catch an error of a fraction of a percent. Through it all, the mystery deepened. The edge's dip was not vanishing under scrutiny. If anything, the more it was tested, the sharper the question became. Was this truly the hydrogen of the first stars, colder than it had any right to be? Or was it something stranger, a signal not from the dawn of the universe, but from the unknown fringes of physics itself? The static was being peeled away, layer by layer. What lay beneath would soon either dissolve into the noise of the ordinary, or emerge as one of the most profound revelations in modern cosmology. By the second year after the EDGE's announcement, the anomaly had taken on a life of its own. It was no longer a quiet technical puzzle confined to a small circle of radio astronomers. It was a stone dropped into the still water of cosmology, and the ripples were reaching into every corner of theoretical physics. The original finding, hydrogen gas, colder than any known model predicted during the cosmic dawn, was strange enough. But as months passed, as simulations multiplied and alternative datasets were scrutinized, the implications began to spiral outward, touching questions as old as the universe itself. If this dip at 78 megahertz was real, it was not simply a matter of adjusting a number in a model. It demanded a rethinking of the physics governing the first hundreds of millions of years, and it carried with it the possibility that something entirely unaccounted for, a force, a field, a form of matter, had been shaping the cosmos from the shadows. The most urgent problem was the depth of the signal. In standard cosmology, the hydrogen of the cosmic dawn is cooled primarily by the expansion of space itself, losing energy as its atoms drift further apart. That cooling is offset, to a small degree, by the background radiation left over from the Big Bang, the cosmic microwave background, or CMB, which gently warms the gas. The edge's result suggested the hydrogen had cooled well below that floor. It was as if the universe had a secret refrigerator, a process pulling thermal energy from matter in the darkness between stars. And if such a mechanism existed, it could not be a minor detail. It would be a fundamental part of the cosmic ledger, one that had been missing from the calculations since the dawn of modern cosmology. Dark matter remained the most compelling suspect. Not the silent, purely gravitational dark matter of the lambda CDM model, but a more interactive species, a form that could exchange heat with baryonic matter, cooling hydrogen without leaving other obvious marks on the large-scale structure of the universe. For theorists, this was both exhilarating and dangerous territory. It meant challenging decades of indirect evidence that painted dark matter as inert. It meant opening the door to lighter, more exotic particles, dark matter, asymmetric dark matter, even dark atoms bound by their own version of electromagnetism. Each variant came with new equations, new limits, and new ways of reconciling the EDGES result with observations from galaxy formation, gravitational lensing, and the cosmic microwave background. Some of these models predicted side effects we might one day detect: faint distortions in the CMB spectrum, subtle shifts in the temperature of intergalactic gas, or altered rates of early star formation. Others hinted at testable laboratory signals, the faintest electromagnetic fingerprints waiting in shielded underground detectors. But the escalation did not stop with dark matter. Other hypotheses emerged, each more provocative than the last. A small faction of theorists proposed primordial black holes, relics of the Big Bang, each no larger than a mountain, scattering across the universe. If such black holes were numerous in the early cosmos, their gravitational fields could have subtly altered the motion and density of the gas, indirectly cooling it or changing the timing of the first stars. Some even speculated that the energy emitted by these tiny black holes through Hawking radiation could interact with the gas in ways not yet fully modeled. Another group suggested unknown background radiation, not the high-energy light of quasars or galaxies, but a faint bath of long-wavelength photons, perhaps left over from an even earlier phase of cosmic evolution. If such radiation existed, it could alter the contrast between the CMB and the hydrogen signal, deepening the observed trough without requiring exotic cooling at all. This raised the unsettling possibility that the edge's signal was not telling us about the hydrogen's temperature, but about a hidden light filling the universe. Then there were the boldest ideas, those that ventured into the territory of speculative cosmology. Some spoke of hidden sectors, parallel universes or mirror matter, that could interact gravitationally and thermally with our own. In these scenarios, the early universe may have exchanged energy across the boundaries of reality, leaving behind only the faintest traces in signals like EDGE. Others invoked modifications to Einstein's general relativity, changing how gravity operated on the smallest cosmic scales, subtly altering the thermal history of the gas. Such proposals were met with deep skepticism, but they shared one common thread. If EDGES was right, the universe was colder for a reason, and that reason was nowhere to be found in the textbooks. While theorists debated, observers turned their attention to the broader consequences. If hydrogen was indeed colder, the cosmic dawn may have unfolded differently than imagined. Colder gas would collapse into stars more easily, perhaps leading to an earlier and more intense period of star formation. The first galaxies might have been brighter, more numerous, and more chaotic than simulations currently suggest. This, in turn, could affect the timing of cosmic reionization, the moment when ultraviolet light from early galaxies stripped electrons from hydrogen atoms, ending the Dark Ages. If EDGES was correct, we might have to redraw the entire sequence of cosmic history between the Big Bang and the first billion years. The timelines in textbooks would shift. The birth order of cosmic events would need rewriting. The sense of escalation was not just intellectual, it was emotional. For the scientists involved, this was no longer a quiet investigation. It was a growing realization that the universe might be hiding an entire chapter of its story. One we were only now glimpsing through the faintest trace in the radio spectrum, and yet there was danger in believing too quickly. If this anomaly collapsed under the weight of new data, it would become another ghost signal, a reminder of how icily the cosmos can trick us. But if it endured, it would mean the very structure of our cosmological model, the scaffold on which we hang all understanding of space and time, had a flaw, a hidden fracture running back to the dawn of creation. By the end of that second year, The Edges team had refined their calibration. The theorists had expanded their models, and the independent observers had gathered enough data to begin publishing results. Some confirmed parts of the original spectrum, but none yet matched the depth of the trough. The standoff had begun. The anomaly was no longer merely cold. It had become colder in spirit, a mystery that grew sharper, stranger, and more resistant. Two easy answers with every attempt to resolve it. The scientists now faced a question that was both simple and terrifying. Were they standing at the threshold of a revolution in physics, or chasing a mirage across the frozen plain of the early universe? The EDGES anomaly was, by now, less a single observation and more a gravitational center, pulling into its orbit the most adventurous minds in cosmology and particle physics. It had passed beyond the safe boundaries of known science, drawing forth proposals from the delicate edge where the credible and the extraordinary meet to explain hydrogen colder than the universe should allow. One needed more than incremental tweaks to existing models. One needed new physics, a rearrangement of the unseen scaffolding that supports reality. Dark matter with a hidden hand. Among the earliest and most prominent ideas was that dark matter itself had played an intimate role in cooling the primordial hydrogen. This was not the silent, ghostly matter of the standard model, the kind that passes through planets and people without so much as a whisper. Instead, this was a more tactile form of dark matter, capable of exchanging tiny amounts of energy with ordinary matter. In one family of models, the culprit was milli-charged dark matter, particles carrying a fractional electric charge so small they evade almost every test, yet large enough to feel the faint electromagnetic pull of hydrogen. Atoms, in the frigid emptiness of the cosmic dawn. These dark matter particles could have acted like a vast, invisible coolant, stealing heat from the gas, without leaving a luminous trace. Such a scenario was thrilling for physicists because it bridged to worlds, cosmology, and particle physics. If correct, it meant that the EDGS signal was not just a relic of the first stars, but a direct measurement of the properties of dark matter itself. Laboratories deep underground and detectors buried in Antarctic ice began to quietly adjust their strategies, searching for the faintest spark that such particles might produce. A second light in the darkness. Another theory inverted the problem entirely. Perhaps the hydrogen had not cooled more than expected. Perhaps the background against which it was measured was warmer. The Edges signal depended on the contrast between the temperature of the hydrogen gas and the brightness of the surrounding radio background. If, in the early universe, there had been a second bath of radio waves, stronger than the cosmic microwave background at certain frequencies, the dip could have appeared deeper without requiring the gas to be colder. Some theorists pointed to possible population 3 supernova, the explosions of the very first stars, as sources of this excess radiation. Others invoked more exotic origins, decaying dark matter releasing soft photons, or even relic emissions from processes in the earliest fractions of a second after the Big Bang. If true, it would mean the universe's infancy was bathed not in one light, but in two, a subtle glow we have only now begun to suspect. Primordial black holes and cosmic mischief in the fertile intersection of astrophysics and the exotic. Primordial black holes returned to the discussion. These hypothetical objects, forged in the high-pressure chaos immediately after the Big Bang, could range in size from pebbles to mountains. While most black holes form from collapsing stars, primordial black holes would be ancient, predating any galaxy. If they were numerous in the early universe, they might have subtly influenced the gas in ways still poorly understood. Some could have drawn in surrounding matter, heating pockets of space while indirectly cooling others. Others might have evaporated through Hawking radiation, releasing energy that changed the balance between matter and light during the cosmic dawn. Such scenarios tread a fine line between the plausible and the speculative, but they carry a unique appeal. If primordial black holes exist, they could also help explain the nature of dark matter itself. The mirror universe hypothesis. From deeper in the speculative well came a concept that sounded almost like science fiction: a mirror universe. In this scenario, our cosmos would be accompanied by a shadow cosmos, identical in its physical laws but composed of mirror particles that interact with our own only through gravity and perhaps a few faint quantum portals. A mirror universe could possess its own hydrogen, its own stars, and even its own version of the cosmic dawn, all invisible to us. If, in the earliest epochs, our two universes exchanged even trace amounts of heat or radiation, that exchange might explain the EDGS anomaly. The coldness we measure could be the shadow of another reality's warmth. While almost impossible to test directly, the mirror universe idea is not born purely of imagination. Some extensions of the standard model in particle physics naturally produce such parallel sectors. For now, they remain elegant ghosts in the equations, neither proven nor entirely dismissed. Rethinking gravity more radical still was the suggestion that perhaps it was not matter or light at fault, but gravity itself. Einstein's general relativity has reigned for over a century, but it remains untested in the extreme conditions of the first billion years. A subtle modification to how gravity works on cosmic scales could alter the rate at which gas cooled, the timing of star formation, and the temperature balance of the early intergalactic medium. Proponents of these modified gravity theories argue that the edge's signal may be our first glimpse at a deeper theory, one that could reconcile dark matter, dark energy, and cosmic expansion under a single framework. Critics counter that such changes would ripple through every other part of cosmology, forcing a reinterpretation of data from galaxy surveys to gravitational lensing. In other words, change gravity, and you change everything. The beauty and danger of speculation: for every hypothesis, there were counterarguments. Millicharged dark matter faced strict laboratory limits. Extra background radiation struggled to find a plausible source that would not also leave traces elsewhere in the spectrum. Primordial black holes remained elusive in every search. Mirror universes and modified gravity, while mathematically rich, rested on foundations that could easily crumble under new data. And yet, the allure remained. Each possibility was a key, perhaps the wrong key, perhaps bent or broken, but a key nonetheless, offered in the hope that it might turn in the ancient lock of the universe's first moments, a signal that tests us. What made the EDG as anomaly so intoxicating was not just the mystery of its origin, but what it demanded of science itself. It asked cosmology to be bold without being reckless, to wander far into the forest of speculation without losing the thread of evidence. In conference halls, the conversations swung between exhilaration and caution. Some scientists feared that the anomaly would vanish under future measurements, leaving behind only wasted models and abandoned theories. Others embraced the risk, arguing that such puzzles were the only way to push the boundaries of understanding. The signal was not simply testing our knowledge, It was testing our capacity for wonder and our willingness to challenge even the most deeply held convictions about the nature of reality. The path forward by the third year, the course was set. New experiments, SORAS, PRIZM, LIDAR, and others, were built or upgraded to either confirm or refute the EDGS result. Each would stare into the same deep frequencies, each seeking the same faint dip in the spectrum. If they saw it too, the anomaly would ascend from controversy to discovery. If they did not, the edge's signal would begin its slow drift toward the catalogue of cosmic false alarms. But for now, it remains suspended between those fates, a whisper from 13 billion years ago, asking whether we have the patience, the tools, and the imagination to hear it clearly. The EDGES anomaly was no longer just a signal. It was a challenge. In science, a single detection, no matter how compelling, is never enough. Reproducibility is the currency of credibility, and without it, even the most beautiful finding risks fading into myth. From the moment Bowman and his colleagues published their results in 2018, a quiet but determined arms race began. Around the world, teams prepared their own ears to the cosmos, each hoping to either confirm the faint dip in the cosmic radio spectrum or expose it as a phantom. Why replication was so hard at first glance? One might think checking the edge's result would be simple. Build a radio antenna, point it at the sky, and listen. But the difficulty lay in the nature of the signal itself. It was tiny, a whisper buried beneath a roar. The galactic foreground, dominated by radio noise from the Milky Way, is more than 10,000 times brighter than the signal EDGS claimed to detect. Separating that faint dip from the overwhelming background was like detecting a candle flicker in the glare of a stadium floodlight. Worse, the foregrounds are not constant. They shift as the Earth rotates, as the ionosphere changes with solar activity, and as faint terrestrial interference sneaks in from hundreds or even thousands of kilometers away. Every replication attempt would face not only the same astronomical hurdles, but its own unique set of environmental gremlins. SARAS, a floating laboratory, one of the most intriguing efforts, came from India. Shaped antenna measurement of the background radio spectrum, SARAS, rather than place its antenna on solid ground, where reflections from the Earth can distort measurements. SARAS has floated its entire apparatus on a remote lake in southern India. The water surface acted as a natural absorber, reducing ground-based interference. In early 2023, the SARAS team released their results. They could not confirm the EDGES detection. In fact, their data hinted that the dip seen by EDGES might be an artifact of ground reflections or subtle calibration issues. This was not a definitive refutation, but it was a warning shot, a reminder that extraordinary claims require extraordinary care. PRIZM, listening from the Arctic far to the north, on Baffin Island in the Canadian Arctic. Another experiment was at work, probing radio intensity at Heisey from Marion PRIZM. Its antennas, shaped like upside-down pyramids, sat in one of the most radio-quiet zones on Earth. Here, the air was dry, human presence minimal, and interference rare. PRIZM, single quotes, as location came with its own challenges: brutal winters, logistical nightmares, and the constant battle to keep equipment running in freezing winds. But the Arctic silence was priceless. By 2021, PRISM had gathered its first deep data sets. Analysis was ongoing, but the early indications leaned toward not seeing the deep, sharp feature reported by edges. If the anomaly was real, PRIZM's data would have to reconcile why two of the cleanest sites on Earth were hearing different cosmic stories. Leader. A broader Iran, the New Mexico desert, the Large Bircher experiment to detect the Dark Ages. Leader took a different approach. Rather than a single antenna, Leader used a network of antennas tied into the existing long wavelength array. This allowed it to measure both the global signal and the structure of the foreground with exquisite detail. LED-AS, multi-antenna strategy, offered a key advantage by cross-comparing multiple instruments in real time. It could detect and potentially eliminate systematic errors that might plague a single antenna setup like EDGE. So Leader team was methodical, slow to release claims, determined to avoid the trap of rushing to either confirm or deny. As of mid-2024, their preliminary analyses hinted at a shallower dip than EDGES reported, but the results were still under heavy review. The psychological pressure, the replication race, was not purely technical, it carried a psychological weight. For every team involved, if you confirmed edges, you'd be part of a historic breakthrough, one that could rewrite the story of the early universe and point toward new physics. If you failed to see it, you risked being cast as the group that killed the signal, even if doing so was the more scientifically rigorous outcome in conferences. Researchers walked a careful line. They spoke of tensions between datasets, rather than contradictions, of alternative interpretations rather than errors. The field was small, and burning bridges over an anomaly could make future collaborations awkward at best. Instrumental lessons, whether or not edges survived replication. Its influence on experimental design was undeniable. The anomaly had forced radio cosmologists to rethink how they dealt with instrumental systematics. Design philosophies shifted. More teams began using floating or elevated antennas to reduce ground reflections. Calibration procedures became more aggressive, with constant injection of reference signals. Cross-site verification became standard, with identical hardware deployed to multiple locations to check for REP, ROD, UCIB, ILITY. In some ways, the edges. Controversy was acting like a vaccine, inoculating the field against sloppy methodology by forcing everyone to work harder, cleaner, and more transparently the stakes beyond the signal. This was never just about one dip in the spectrum. If confirmed, the EDGE's anomaly could reshape our understanding of dark matter, cosmic structure formation, and the physics of the early universe. If refuted, it would still have value, a case study in how difficult it is to extract truth. From the edge of detectability, the replication race was, in the deepest sense, about the credibility of observational cosmology itself. In an era when billion-dollar telescopes like JWST and SKA were being built, the community could not afford the perception that its most headline-grabbing results were artifacts of poorly understood equipment, waiting for convergence by late 2024. The results from SARA's, PRIZM, Leader, and others were converging, but not yet perfectly aligned. The deeper, sharper edges dip was appearing increasingly lonely in the data landscape. If the final verdict fell against edges, it would not be a death blow to 21 centimeters cosmology. Far from it. Instead, it would clear the way for cleaner measurements, ensuring that when we finally do catch a cosmic whisper from the first stars, we will know it beyond doubt. For now, the sky remains patient. Its signals are still there, waiting. The only question is whether we will hear them clearly, and whether we will know what they truly mean. The race to replicate the edges anomaly had scattered antennas across deserts, tundras, and remote lakes, all straining to catch the same faint note from the universe's infancy. Now, years later, the results were finally converging, and the picture they painted was complicated. The weight of the question at its core, the edge's signal, was not just a technical curiosity. If it was real, it meant something profound had altered the cooling of primordial hydrogen. Perhaps an interaction with dark matter itself. Such a claim would ripple far beyond cosmology, touching the foundations of particle physics. But extraordinary implications demand extraordinary certainty. The question was simple. Did the signal exist? The answer was proving anything but. The first cracks, the earliest signs of trouble, came from Saras, its floating antenna, gliding on the mirror-still waters of a remote Indian lake, had been designed specifically to suppress ground reflections. One of the main concerns critics had raised about edges when the Saras team released their 2023 results. The verdict was cautious but clear. They found no evidence of a deep, narrow absorption feature. At 78 MHz, their data fit more comfortably with a shallower signal, one consistent with standard astrophysical models. Saras went further, publishing a detailed analysis of how subtle ground plane effects in the EDGS setup could have mimicked a cosmic signal. It was not an accusation, but the implication hung heavy in the air. Silence from the Arctic meanwhile. PRIZM's antennas on Baffin Island had been listening through the long Arctic nights. Their location offered one of the purest radio skies on Earth, far from FM transmitters, cell towers, and the restless ionosphere of lower latitudes. Yet, when PRIZM's preliminary analysis emerged, the result was striking in its absence. They did not see the same pronounced dip reported by edges. Their spectrum was smoother, more in line with theory and less dramatic. If Edges was hearing a choir from the early universe, PRIZM was catching only the faintest hum. The leader cautioning. The New Mexico desert leader had taken its time. Its multi-antenna approach gave it a unique advantage, the ability to map and subtract foregrounds with a precision single antennas could not match by mid-2024. LED-AS data leaned toward the same conclusion as Saras and Prism. Any global 21 centimeters. Absorption feature was shallower than EDGS claimed. But LED-AS scientists resisted a clean, binary declaration. They knew too well that non-detections could stem from subtle differences in methodology, calibration, or environmental factors. They did not accuse. They simply measured and let the numbers speak. The Edges defense all the while the Edges team stood by their finding. Bowman and his collaborators published additional analyses, refining their calibration and exploring in exhaustive detail possible sources of systematic error. They acknowledged the challenges, but argued that none of the proposed instrumental effects could fully account for the depth and shape of their signal. They also pointed to the possibility that different instruments, in different environments, might respond differently to the complex interplay of sky, ground, and atmosphere. If Edges was right, history would vindicate them. If wrong, they would have been the spark that drove the most rigorous era of 21 centimeters cosmology yet. The psychology of consensus. By late 2024, the field was settling, not with the explosive certainty of a single decisive paper, but with the slow gravitational pull of collective judgment. Conferences no longer buzzed with urgent EDGES debates. Instead, the anomaly was framed as a valuable case study in the difficulty of extracting truth from the cosmic noise. Young researchers still cut their teeth on the Edges dataset, testing new foreground subtraction algorithms or novel calibration schemes. But in grant proposals and roadmaps, the community's focus had shifted toward the next generation of instruments, Hera, Scolo, and Reach. The verdict was not an official refutation, but the center of gravity had moved. The majority of evidence now leaned toward the EDGES signal being an artifact, the human element for those involved. The outcome was bittersweet. Science is often portrayed as a march toward truth, but in reality, it is a landscape of blind paths and false peaks. Some in the Edge's camp felt the criticism had been too quick, too sharp. Some in the replication teams felt their caution had been overshadowed by a media narrative eager for a cosmic dawn headline. Yet, beneath the professional rivalries, there was also respect. All sides knew how hard it was to listen to the universe at these frequencies. All knew how easily a whisper from 13 billion years ago could be mistaken for a trick of the instrument. Legacy and lessons. Even if the EDGS signal fades into history as an artifact, its legacy is profound. It triggered a global mobilization of experimental ingenuity. It pushed calibration techniques to new heights. It forced an honest reckoning with the limits of current technology. Most importantly, it reminded the field that failure to confirm is not failure at all. It is the very process by which science protects itself from wishful thinking. The universe, whence the first stars are still out there, their photons still rippling across the void, their story still written in the faint glow of neutral hydrogen. The next instruments, quieter, sharper, more immune to the tricks of Earth's surface and atmosphere, will hear them. And when they do, the detection will stand not because it is beautiful, but because it has survived the crucible of replication. In the end, the Edge's saga may not be the story of a discovery, but of a discipline learning how to listen better. The cosmos has been speaking for nearly 14 billion years. It can wait a little longer for us to get it right. The Edge's signal, whether artifact or revelation, was never meant to be the final word. It was a door left ajar, a faint suggestion that the universe's first chapter could be read not in starlight, but in the whispers of hydrogen now, with the lesson of EDGES etched into the discipline. The field is preparing for a leap forward. Not a lone antenna in the desert, not a single instrument straining against the noise, but an armada of new observatories, each engineered with a precision that would have been unthinkable 2 decades ago. From a dip to a matha, global 21 centimeters signal, the single spectrum Edges sought to measure is only the simplest layer of the story. Beneath it lies a tapestry of spatial fluctuations, tiny variations in brightness that trace the growth of structure, the clustering of matter, and the birth of the first galaxies. Mapping these fluctuations would transform cosmology. It would not only confirm when the cosmic dawn began, but show where and how the first light spread across the universe. Instead of one dip on a graph, we would have a movie, a time-lapse of the cosmos awakening. Hera listening with 1,000 ears in the dry Karoo Desert of South Africa. The hydrogen epoch of reionization array, Hera spreads across the landscape like a frozen constellation. Its 350 dish-shaped antennas work in concert, turning the night sky into a three-dimensional map. HERA's design is uncompromising. The dishes are fixed, staring straight up, optimized to minimize ground reflections. An instrumental systematics. Its computing backend is built to handle the torrent of correlations between antennas, the raw material from which detailed sky maps will be carved by the end of its survey. Hera aims to measure the statistical fingerprint of neutral hydrogen between redshifts 6 and 20, charting the entire reionization process. It will not just confirm the cosmic dawn, it will dissect it. Ska Low, the giant awakens farther east. On the remote plains of Western Australia, the square-kilometre array, low-frequency component is preparing for construction. When complete, Ska Low will dwarf all its predecessors. More than 130,000 antennas spread over 65 kilometers, working together as the most sensitive low-frequency radio telescope ever built, where EDGES could only infer a single scale. Brightness, temperature, SKLO will image the 21 centimeters signal directly. Its sensitivity will be so great that, in principle, it could detect the ionized bubbles around the first galaxy's individual structures from a time when the universe was less than 1 billion years old. With Ska Low, the age of speculation will end. The cosmic dawn will become an observational science, reach engineering out the uncertainty even before Ska Low's first antenna is switched on. A smaller, highly specialized instrument is already hunting the global 21 centimeters signal with a radically new approach. The radio experiment for the analysis of cosmic hydrogen, REACH, in the Karoo Desert has been designed from the ground up to eliminate the calibration pitfalls that haunted edges. REACH's key innovation is its model-agnostic signal extraction. Instead of assuming a specific foreground shape, it uses Bayesian statistics to separate cosmic and terrestrial contributions simultaneously. Its antenna is engineered to be spectrally smooth, reducing the risk that subtle instrumental ripples could mimic a cosmic feature. If REACH detects a signal consistent with theory, it will be the cleanest confirmation yet of the cosmic dawn. If it finds nothing, it will place the strongest limits so far on early universe physics. Global synergy. The coming decade will not be a story of a single hero experiment. It will be a symphony. Hera delivering statistical power over wide redshift ranges, Ska Low producing direct images of the evolving hydrogen field, REACH refining the global signal search, PRIZM, SARAS, LIDAR, and successors continuing to refine methods and cross-check results. Together, these instruments will cross-validate each other's findings, weaving a coherent narrative from independent approaches. For the first time, cosmologists will be able to anchor their models in a continuous, well-measured timeline from the end of the Dark Ages to the full ionization of the universe. The stakes. Beyond cosmology, the payoff will extend far beyond understanding the first stars. The 21 centimeter signal is sensitive to processes invisible to any other probe. If dark matter interacts even weakly with normal matter, its fingerprints could be imprinted in the timing, shape, or depth of the signal. Similarly, exotic heating mechanisms, from early black holes to decaying particles, could alter the hydrogen temperature in ways that betray new physics. In this sense, 21 centimeters cosmology is not only about astronomy. It is a potential testbed for particle physics at energies impossible to reach on Earth. Patience written in starlight, the great irony is that the signal has been there all along, drifting toward us for over 13 billion years. The challenge is not in its absence, but in our ability to hear it. Every new generation of instruments narrows the gap between the cosmos and our understanding. Every refinement and calibration, every algorithmic breakthrough, every cross-checked dataset brings the first dawn into sharper focus. It is not a sprint. It is a slow, deliberate turning of the universe's first page, A future remembered when the first detailed 21 centimeters maps are finally unveiled. They will show a universe in transition, pockets of light blooming in a sea of darkness, ionized spheres expanding, merging, reshaping the cosmic web. The fingerprints of the first black holes and the earliest galaxies, preserved like fossils in hydrogen's faint glow. And when historians of science look back, they will remember the path that led here, including the false starts, the contested claims, the experiments that were wrong in detail but right in ambition. Edges may or may not be remembered as the first detection of the cosmic dawn, but it will be remembered as the experiment that made the field believe it was within reach. The universe's first sunrise is coming into view, not tomorrow, not next year, but soon, on the timescale of science, which is measured not in news, cycles, but in the patient accumulation of certainty. And when we finally see it, it will not just be the dawn of the universe we are witnessing. It will be the dawn of a new way of listening, one that can carry us farther into cosmic history than we have ever gone before. In the beginning, there was no sound, only a perfect darkness, heavy and unbroken, filling every horizon. Then, not an explosion, but an unfolding, space stretching, cooling, shaping the raw ingredients of reality. Hydrogen and helium settling into a vast, silent ocean. For hundreds of millions of years, nothing stirred, no stars, no galaxies, only the cold breath of an infant cosmos drifting outward, and then the first light, born not in a blinding instant, but in fragile flickers. The earliest stars, forged in the deep, set the darkness ablaze. They burned with a heat fierce enough to change the chemistry of the universe itself. They carved ionized islands in the hydrogen sea, scattering photons that had waited since the dawn of time to move freely. The echoes of that awakening, faint, stretched, almost erased by expansion, still cross the void today. They pass through us as they pass through every world, every star, every drifting particle of dust. They are not lost, only waiting for ears sharp enough, patient enough to hear them. For most of human history, we could not. Our lives were brief, our tools small. But in the span of a few generations, we have taught metal to listen. We have taught algorithms to see in radio's invisible light. We have learned to filter out the noise of our own planet so that the voice of creation can speak. Each experiment, from the lonely antenna in the desert to the sprawling arrays on the plains, is a kind of act of faith. Faith that the universe has left us a record. Faith that we can read it without erasing it in the process. Perhaps the most humbling truth is this: the story of the cosmic dawn is not ours alone. It belongs to the atoms in our blood, forged in stars that were themselves descendants of that first generation. It belongs to the space between galaxies, still carrying the signal of its birth. When we map the first light, we will not only be looking outward, we will be looking backward through time and inward, toward the origins of everything that has ever lived. And someday, maybe decades from now, we will hold in our hands the first complete portrait of the universe's awakening. It will be beautiful, but it will also be unfinished, because every answer will raise new questions. That is the nature of listening to eternity. There is no final note, only a deeper silence inviting us to lean closer, and we will, because we are not only creatures of fleeting moments. We are the ones who remember to listen.